Hello viewers, this is a question of CS MAIN 2011 Mathematics Paper 2 of Operations Research Dual and its graphical solution. Question is, write down the dual of the following LP problem and hence solve it by graphical method. So question is, minimize z is equal to 6x1 plus x2 and constraints are 2x1 plus x2 is greater than equal to 1, 3x1 plus 4x2 is greater than equal to 1.5, x1 x2 are greater than equal to 0, and this question is of 20 marks. First we would like to write down the primal problem in standard equation form, and this is the standard equation form. Minimize z is equal to 6x1 plus 4x2 and constraints are 2x1 plus x2 minus x3 is equal to 1. Here x3 is surplus variable because we can see constraints are of greater than equal to sign. So constraints are having surplus, so minus x3, and similarly the second constraint is 3x1 plus 4x2 minus x4 again surplus variable is equal to 1.5. In the objective function we can write down plus 0x3 plus 0x4 and x1, x2, x3, x4 are greater than equal to 0. So this is our primal problem in the standard form, equation form. Now we write down the dual of the problem. So we take w as a variable with respect to z, and because this is minimization problem, so we write down dual in maximization, and with respect to two constraints we take y1 and y2, two variables. So to write down the objective function of the dual, we write down maximize w is equal to right hand side of the constraints of the primal are 1 and 1.5, so 1 y1 plus 1.5 y2, and constraints are, we look the first column of the constraints of the primal. Here coefficients of x1 are 2 and 3, so the first constraint for dual is 2y1 plus 3y2 is less than equal to 6. Here 6 is the coefficient of x1 in the objective function of the primal, and sign we have taken less than equal to because it is a maximization problem of dual, so this will be less than equal to. To write down the second constraint of the dual, we look at the second column of the primal. Here coefficients of x2 are 1 and 4, so 1 y1 plus 4 y2, again sign is less than equal to due to maximization problem, and 4 is the value which is coefficient of x2 in the objective function of the primal. Now we look at the third column, which is minus x3. So, and there is no x3 in the second constraint, so we write down minus y1 less than equal to 0. And similarly for fourth column, coefficient is minus 1, so minus y2 is less than equal to 0. It implies y1, y2 is greater than equal to 0. So this is our dual of the primal problem. Now we would like to solve this dual with the help of graphical solution. But before that, I would like to give you duality theorem statement, which states that if the primal problem has an optimal, then so has the dual, and they both are equal. Zp is equal to zd, that is z primal is equal to z dual. And it states if primal is unbounded, then dual is infeasible. And second is, if primal problem is infeasible, then the dual is either infeasible or unbounded. So these statements may help us to decide the solution of the dual. Now we draw the constraints of the dual. So first constraint of the dual is 2y1 plus 3y2 is less than equal to 6. We find out the values of y1 and y2. We substitute y1 as 0 and we get y2 as 2. We substitute y2 as 0, we get y1 value as 3. And for second constraint, we substitute y1 0, we get y2 1. We substitute y2 0, we get y1 4. Now we plot these values and we see the graph is here. We get this picture and we can see this dashed region is feasible region and corner points are 0, 0, 3, 0, 12 upon 5, 2 upon 5. This we have got after solving the constraints equations, and 0, 1. Now we got the extreme points of the feasible region. We find out W value at these points. At 0, 0 this is 0, at 3, 0 this is 3, at 12 upon 5, 2 upon 5 value of W is 3, and at 0, 1 it is 1.5. So maximum value of W is 3 on the line segment CD. So this is our value of W, which is 3 with the extreme points 3, 0 and 12 upon 5, 2 upon 5. Now if we see the minimum value of Z, that will also be 3. Thank you.